So, hello everyone and welcome to Wallah guys. Hope you all are doing well and your preparation is going to up to the mark. Now guys, we are in, we are dealing with the comprehensive course of signaling system in which we have covered till now the step functions, elementary functions. And now from the today's class onwards, we are going to cover impulse function, which is one of the most important topics. Okay. Hope you are revising all the concepts. Those who haven't started this series, I don't know what they are waiting for, but the point is that please go and cover each and every concept from the playlist itself. If you start the playlist from that's today's itself, or let's say from after 2 days or 3 days, enjoy your Saturday weekends, Saturday and Sunday, then you will be definitely benefited by these kind of series. If my voice and visibility, if everything is clear, then we are going to start. First, let me know. And myself, Pankaj Singh, in this field, I have nearly 15 plus years of teaching experience. So please, before starting the class, let me check from my end also that whether this audio and video is clear to me or not. So let's see. Okay. So hello everyone. If anyone is present there, then please. Yes. I think audio and video is clear. It is visible to me and it's audible to me. Okay guys, so let's start. Now the today's topic is impulse function. What we covered till now is that is we have covered elementary functions. We have just started the elementary functions. Okay. And we have covered step function in detail. Step function. Okay. Now we are going to cover that is the impulse function in today's class. That is in today's class what we are going to cover, that is the impulse function. Okay. And mainly the impulse function that we are going to cover is the CTS part, continuous time system. Okay. And here we are going to cover this CTS part. Okay. And the DTS part we will cover in the next class, that is the next lecture, and in which I will cover the discrete step functions also. I haven't covered the discrete step function till now, though I have covered a continuous step functions, but discrete step function is not covered. That we will cover just a small topic of 15 to 20 minutes. Okay. So I will cover the discrete step function after that is this impulse function. Okay. Hello Amrita. Hello, good evening Mandavi. So let's start now. Question is that what do you mean by the word impulse? What is impulse? See, you often heard about that a particular person, let's say X, have impulsive response. If someone, let's say, disturb him or her by just little amount, the reaction that is coming out is very large. The nature is impulsive. Yes or no? So what do you mean by the word impulse? See here, impulse means a shock, a basic shock that is exists only for momentarily amount of time, very minute amount of time, and it has an impact which is very large. The impact is very large. That's what the meaning of impulse in day-to-day life. In our signal processing also, the impulse function is a function. Let's say consider we have let's say a step function. Okay. Suppose I have a step function. Suppose I have a step function like this. Okay. And let's imagine that we have a step function from, let's say, minus tau by 2 to tau by 2. This is a rect function, forgive my drawing. Okay, to tau by 2, and this is having the height of 1 by tau. Suppose I have this function, a function which exists, which is a rectum. How will you write this function? I will say that it is x of t. Let me call this as a x of t. Let me call this as a x of t. Then x of t is 1 by tau rect t by total width is how much? What is the total width? The total width here is, see, this is the width, this is the total width, and the total width is tau. So 1 by t rect t by tau. So this is the function 1 by t rect t by tau. Now what I am doing is that, see here, the width I am going to reduce. Okay, the width I am going to reduce. Let me first okay, what I am doing is that, see here, I will reduce the width and increase the height by maintaining the area under the curve. What is the area under the curve of this function? See here, the area under the curve of this function is a is 1 by tau into tau is 1. That's what my area under the curve is. Now what I am doing is that, see here, I will reduce the width tau and increase the height in such a way that the area under the curve will remain a constant. So how will you perform this one? See here, suppose what I am doing is that I am, okay, I will maintain like this one, see, so that the width here is tau dash by 2 to tau dash by 2, and this is 1 by tau dash. Still the area is same. Same here also. Same here. Let us consider this one. Okay. Now this one is same, tau double dash by 2 to tau minus of tau double dash by 2 plus tau of double 1 by tau dash. All this function, good evening Vijay. In all this function, what I am doing is that, see here, I am decreasing the width and I am increasing the height. Now what will happen if you go on like this? If you go on like this, then see, the point come will be like this. See, the width is increased, width is decreased to be 0, but the height is increased to be nothing but a very large. Say a time come, let's use this, a time come when we have a very small width. See, look, very, very small width. Okay, like this. Yes, see, this is the function. This function is having a very small width, very, very small width, but very large height, and hence this function is having still the area. Let me call this as let's say tau s minus of, and it is minus plus tau s, and it is tau s, sorry, and this is 1 by tau s. Okay, this is 1 by tau s, so that area still is, that is tau s into 1 by tau s by 2, so that it is still a 1. So this function, when you reduce when we decrease the height to be ideally approaching towards 0, and the width is the width is ideally approaching towards 0 and the height is approaching towards infinitive, the function is said to be exist only for a small amount of time. And how I will, let's say, model this function, I will say that I have a function, okay, I have a function which is like this, see here, which is like this, which exists for, let's say, which exists for a momentary amount of time. Let's see, like this. Okay. So what I'm saying is that this is a function which only exists for 0 amount of time, but its height is ideally approach towards 0, approach towards the infinitive. So this function we call it to be the impulse function. And how we denote the impulse function? We denote this impulse function by delta t. So mathematically speaking, hello Pratiksha, mathematically speaking, the delta t is nothing but my infinity at a t is equal to 0 and is 0 else. And 0 else, okay? So this function is ideally approaching having a value of infinitive, but the width is ideally 0. This is only exists for 0 amount of time. Though it's not possible, we always have some finite width. We never have a function which exists for 0 width. It's not mathematically possible. But hypothetically what I'm saying is that it is a function which only exists for 0 amount of time and it have a height of infinitive. But one thing is very clear, that minus infinitive to infinitive, if you take delta t dt is equal to 1. So this function I am denoting it by delta t, this function having the finite area. So what I am saying is that this is a finite area function. That's what the very important point is. Okay, so this function is a finite area function. It's not a function which is denoted by a height. It's not a function which is denoted by a height. It is a function which is denoted by its area. So how will you write? See, mathematically we will write delta t in this way. Delta t is 1 at t is equal to 0 and is 0 else. But this 1, mind it that, see here, this one is actually, this one is area, not the height. Okay, this one is nothing but my area of this function, and this point is of course very clear that it is minus infinitive delta t dt is equal to 1. Okay, minus infinitive delta t dt is equal to 1. So what I am saying is that this is a function which I am representing by the area function. This is a finite area function. Okay, so if you have, let's say, k delta t, or let's say some constant delta t, then the area is not equal to 1, its area is equal to that particular constant. For example, if I have, this is this part, let me box it, this part, and I have told you this part, okay. If I have a k delta t on the other hand, then k delta t is denoted by k at t is equal to 0 and is 0 else. But what is important is that minus infinitive k delta t dt is equal to k. So that's what the very important point is. So this is a function which is denoted by having a not unit area. If it is a unit area, it's a unit impulse function. It is nothing but my what? It is a impulse function having a area under the curve equal to k, or strength of k, having a strength of particular k. Okay, fine. This is what my impulse function. This exists only for t is equal to 0. Okay, this exists only for t is equal to 0. That's a axis t. That's the axis t. Fine, that's okay. But sir, can you tell me where I encountered this impulse function? See here, where I encountered this impulse function. Listen carefully now. Suppose I have let's say a step function. Suppose I have a step function. Okay. Suppose I have this is a step function. Suppose I have this is a step function. Okay, this is ut. I'm calling it to be ut. I'm calling this to be ut. Okay, now my point is that, see here, if this is the unit step function denoted by ut, then I told you in the last class that ut is 1 for t greater than 0 and is 0 for t less than 0. It is undefined. It's actually 1 by 2. It's the practical value we are taking to be 1 by 2, but it is actually undefined at t is equal to. So at t is equal to 0, we will say that it is undefined. At t is equal to 0, the function is undefined. So this function is undefined at t is equal to 0. This is what the t curve is. But suppose someone asks you that, sir, can you find out what is the, let's say, I will say that what is d by dt of a function at this point, at t is equal to 0. What is d by dt? What is d by dt of ut? See, this is a constant one, so constant derivative is 0, that I know. But what is, since the function itself is not defined at t is equal to 0, since the function itself is not defined at t is equal to 0, so what is the derivative of this function at t is equal to 0? Listen carefully. See, the derivative formula, if I say that d by dt of x of t I have, then I know that it is xt plus h minus xt divided by h with h tends to 0. Okay, this is the first approximation formula for derivative. This is the first approximation formula for derivative. Now listen carefully. Let's box this first. This is the first approximation formula that I am using. See here. Suppose if I consider this point, here, let's take different color here. So if this is a point, let's say 0, then this is a point 0 plus, and somewhere here we have a point 0 minus. So if I considered this to be, let's say 1, xt plus h is 1 minus, let's say 0 divided by h with h tends to 0. Okay, so when you take the gap between 0 minus and 0 plus, this is ideally 0. So this comes out to be, if you put h is equal to 0, this comes out to be infinitive. So the derivative of this function at t is equal to 0 is ideally infinity. Okay, so whenever you have a point of discontinuity, if you take the derivative of a function at the point of discontinuity, then it comes out to be infinitive. So instead of representing it to be the infinitive, we say that since impulse also is an infinitive function, why not represent the derivative to be equal to d by dt of ut to be equal to delta t. Okay, so what I am saying is that instead of representing this function because everywhere this is constant, so derivative of constant is equal to 0, but the point is that what is the derivative at t is equal to 0? So when you take d by dt of ut, it comes out to be delta t. It is nothing but my impulse function, which is represented by infinitive. So if someone asks you, let's take this function, say for example someone asks you this function, okay, suppose I have this function and this is having a height of 5, this is x of t. Question is that plot d by dt of of x of t, then we can plot. See here how we will write this x of t. How we will write this x of t? X of t, I told you in the last class that x of t is, let's count to be 0 and 2. So I have two jumps. See, this is the jumps. So I will write 5 ut minus 5 u t minus 2. 5 ut minus 5 ut minus 2. This is what my x of t is. Okay, so what I am saying is that, see here, if you take the derivative of this function, if you take the derivative, then everywhere, since it is a constant, so the constant derivative is equal to 0, but it exists at t is equal to 0 and t is equal to 2. So let's plot the derivative. The plot of derivative is very simple. It is like this. See, okay, the plot of derivative is very simple. It is like this. See, first we have a derivative at 0 with a height of 5. See, upper value minus lower value. So this is having a height of 5 like this. There is a one derivative at t is equal to 0, and there is another derivative at t is equal to 2. And what is the height of this function? Upper value is 0, lower value is 5. 0 minus 5 is what? Minus 5. Okay, so I am saying that this is having a height of 5 and this is having a height of minus 5. So what is the derivative of this function? So I will write d by dt of x of t can be written as what? It is 5 delta t minus 5 delta t minus of 2. 5 dt, 5 delta t minus 5 delta of t minus of 2. That's a very simple, that's a very, very simple representation of this function. So this is x of t and this is the plot of what? d by dt of x of t. This is the plot of d by dt of x of t. Okay, so whenever there is a jump at the point of discontinuity, if you derivate the function, if you derivate the function at the point of discontinuity, then surely you will get an impulse function. Anywhere you have a jump, if you take the what? If you take this one, that's d by dt of x of t, then you will get this as a jump. You understand my point or not? Hello? So that is one of the very, very important point that you have to take care of. That is one of the most important point that you have to take care of. Okay? Now, so this is what the d by dt of x of t is. Now, I am giving you homework that plot this function, sorry. Plot the d by dt of this function. Let us consider this to be 0, this is 2, that is 4 and that is 6. This value is minus 5, this value is 5 and that value is 8. Question is that plot d by dt of x of t. Plot d by dt of x of t, easily you can plot. Okay. So that's what the derivative part and how we encountered this impulse function. What is the impulse function? What is the definition of impulse function? Where we get the impulse function? What is the physical significance of the impulse function? That I have covered till now. Okay. Now next is that let's play with the impulse function. Suppose we have, that is the next topic is operation on impulse function. Okay, let's see. Suppose we have a impulse function which is delta t. I know that how delta t's look like. Delta t is the function which exists at t is equal to 0. Having a strength of, mind it that this is not its value, it is the area in the curve. So delta t is, just now we have covered, it is 1 at t is equal to 0 and is 0 else. So this is the point that we have covered till now. Now listen carefully, delta t is 1 for t is equal to 0 and 0 else. Suppose I want a delta, what is important thing is that area under the curve minus infinity to infinitive delta t plus delta t dt, okay, it is equal to 1, that I have covered. Now the point is that what is delta t plus alpha? Can you represent this delta t plus alpha, or can you represent delta t minus alpha? Yes sir, easily we can do it. See here, what is delta t plus alpha? It is a function, this is 0, it is a function which exists at minus alpha, okay, and this function, it is a function which exists, let's say, which exists at alpha, which exists at alpha. So this is the right shifted version of impulse function, this is the left shifted version of impulse function. Let me call it as a and this we call it as a b. Easily we can plot delta t plus alpha and delta t minus alpha in this function. Now my question to you is that, see here, what is area under the curve of delta t plus minus of alpha dt? If we know that area under the curve of impulse function is equal to 1, then what is the impulse function of shifted? What is the area under the curve of shifted impulse function? Easily we can find out. How? So put t plus minus of alpha equal to, let's say, some variable p. Now since alpha is a constant, what is the alpha? Alpha is belongs to the real constant, yes or no? Alpha is a constant, so t plus minus alpha is just a constant, so dt, what is dt then? dt is equal to dp. Why? Because if you integrate, if you differentiate this, then dt, since it is a constant, it comes out to be 0, and since t is positive, limit will not change, limit will remain the same. So this means that what it looks like, it is minus infinite to infinitive delta p dp, okay. Now if you compare this with this equation, then there is just a change of variable, meaning is exactly same, there is just a t here, there just a p here, change of variable here, and hence this is also equal to 1. So what is the result that I'll get? I'll get that if we have a shifted impulse function minus infinity to infinitive delta t plus minus of alpha dt, then this is also equal to 1. This is also equal to 1. That is one of the most important point that you have to take care of. So shifted impulse function also have area in the curve equal to 1, that we use in today's class. So delta t plus minus of alpha dt is equal to 1. Okay. Next point. Next point is, let's consider, see here, suppose scaling on. Scaling. Question is that, what is delta of alpha t? That's one of the very important point. What is delta of alpha t? Let's how we define for this, the answer of this function can be dealt by its pure definition. See here, how we define the impulse function. See, we said that if we consider a rect function, let's say, having let's say it is from minus tau by 2 to tau by 2, and this is having a width of height of 1 by tau, this is having a height of 1 by tau, then see here we said that if this is the width, if this is the, let's say, width up to this one, having a width of tau, then what I'm saying is that, see, 1 by tau into tau, 1 by tau into tau will gives me 1. That is, if a function tau tending towards 0, if we put tau tending towards 0 here, then this function becomes an infinitive, this function becomes a 0. Though infinitive, don't say that infinitive into 0 is an indeterminate form. I'm not using indeterminate form, I'm saying approaching towards. I'm not making equal to 0. So don't say like that, this function becomes the infinitive, this function becomes a 0. What I'm doing is that, listen carefully, simply I'm approaching tau to be 0 so that the width, height will go on increasing and the width will go on decreasing, so that the overall product that we get is nothing but my what? Is a constant. Now what I'm doing is that, consider this to be x of t. So what I'm saying, that this is what? 1. So 1 is the area, so I'm representing this area by an impulse function delta t. Instead of writing it to be 1, I'm representing it to be a impulse function. Now question is that, suppose for example, if I scale this function, then what will happen? If I scale this function, then what will happen? You know that if you scale any function x alpha t, then I told you in the very first class, go and revise these classes, that alpha will come into the denominator. Okay, so if you scale this function, then what we will get is a function which is minus tau by 2, it is 1 by tau. Hello. Okay, very good evening. Minus tau by 2 to tau by 2. And what I am saying is that, see, listen carefully, if I scale this by alpha, if suppose I scale it by alpha, then this comes out to be this one. This comes out to be in denominator. Okay, scaling factor comes out to be denominator. Now let's find out the area of this function. So area A is what? It is what? The total width. Total width is what? Tau by alpha into 1 by tau. This is what the area is. This is what the area is. Tau by alpha into 1 by tau, with tau tending towards 0. Okay. Hello. So what I am saying is that, see, listen carefully, this I am denoting this to be an impulse function. So if I denote this to be an impulse function, okay, so not 1 by tau, it's, listen carefully, this to be tau. Okay, height is tau, no? Sorry, I did a fundamental mistake here. This is tau. Then only, see, the total width is no. This is 1 by tau only. 1 by tau. Yes, 1 by tau only. This is 1 by tau only. See here, total width is tau by alpha, and tau cancel with tau tending to a 0. What I am saying is that, see here, this thing, this, whatever with the circle part, see, tau into 1 by tau with tau tending towards 0. Tau into 1 by tau, tau into 1 by tau with tau tending towards 0. I am denoting it by impulse function delta t. So I am denoting the whole function to be impulse function. It is equal to 1 by alpha times delta t. Hello. See what I did. I said that this is what the impulse function is. See, if you decrease the height, if you decrease the width and increase the height like this, then what will happen? Then time comes that it will approach towards 0 and so on. What I am doing is that I did the scaling on this factor. So if I scale this factor by alpha, then the what change in the area I am getting? See here, what is the change in the area that I will get? See, it is tau by alpha. Total width becomes tau by alpha. It is 2 tau by alpha 2 tau by 2 alpha, so 2 cancel, tau by alpha is the width, and height is 1 by tau. Now what I am saying is that 1 by tau into tau with tau tending towards 0, I am denoting it by a delta t. So let's call the whole thing in delta t, but 1 by alpha terms will come into the picture. So what I get till now is that, see here, what I get till now is, see, what I get till now is, listen carefully. Okay. Listen. So what I get till now is delta of alpha t is 1 by alpha delta t. 1 by alpha delta t. Hope you understand the derivation. What I did is simply understand the point. What I am doing is I just do the scaling factor, and this factor 1 by alpha will come into the picture when we scale it. So 1 by alpha times delta t I will get, 1 by alpha times delta t I will get. But the point is that, see, listen carefully, I am saying that this function is, if suppose I reverse it, what will happen if alpha is negative? See, if alpha is negative, since this function is purely even means that if you reflect both the sides, it's just a mirror image of both the sides. So it will purely overlap on both the sides. So if it is purely overlapping on both the sides, this means that reversal will have no effect. Is it clear? Since this is a purely symmetrical function in both the sides, in both the quadrant, so reversal has no effect. This means that, see, if I'm saying that alpha, if let's say delta of minus 2t is also equal to 1 by 2 delta t, because reversal will have no effect. To denote this, what I'm doing is that I am denoting a mod on that, so that it says that if you, let's take a reversal on both the sides, then the point is exactly same. The point is exactly same. So delta of alpha t is equal to nothing but my what? What I get? I get 1 by mod alpha times delta t. That's one of the very, very important point. Let me write separately somewhere. Delta of alpha t is equal to 1 by mod alpha times delta t. So technically I derive this one, but not in a mathematical way, in the heuristic way. Heuristically we can derive. Heuristically means just by intuition, just by our knowledge, I derive this delta of alpha t to be 1 by mod alpha delta of t. Mind it that u alpha t, in the last class you tell that u alpha t was ut if alpha is greater than 0, and u alpha t is u minus t if alpha is less than 0. This is the another term that we have derived in the last class. But scaling on impulse will come on to this. Mind it that what is the now, what change? If you take the area in the curve, then this 1 by mod alpha will come outside. This means that the area is now multiplied by the factor 1 by mod alpha. That's what the meaning of this complete expression is. So area is not 1 now. If you take delta 2t, delta 3t, delta 4t, or let's say any other thing, then this area will now model to 1 by mod alpha. Okay. Now let's consider this one. See. So let's combine operation. If suppose someone asks you what is delta of alpha t plus beta, you know that delta t exists at this function. Delta t exists at this function at t is equal to 0. Delta t exists at t is equal to 0. Okay. So the point is that what is delta of alpha t plus beta? Listen carefully. It is delta. I am taking alpha to be common. It is t plus beta by alpha, like this. Okay. Now the point is that, see here, delta of alpha, just now we have covered, it is a 1 by mod alpha delta of t plus beta by alpha. So the whole thing is now shifted to minus beta by alpha, an impulse function whose actual height is now not 1, instead, not height, area in the curve is 1 by mod alpha. Okay, this is what the representation of an impulse function is. This is what the representation of an impulse function is. Okay, so shifted impulse function means all things we have a impulse, we have, let's say, scaling factor, we have a what, shifting factor, maybe it is negative. Let's take an example. Suppose I have suppose I have delta of minus 2t plus 4 plot. So we can easily plot, it is delta of minus 2, it is t minus 2. So 1 by mod minus 2, it is 1 by mod minus 2 delta of t plus t minus 2, it is equal to, which is equal to 1 by 2 delta of t minus of 2. So this is the function which is represented by here. Okay, so if you take the area in the curve of this function, if you take the area in the curve, minus infinitive to infinitive delta of minus 2t plus 4 dt, then what you will get? You will get 1 by 2. Because the whole thing is this one, see, it is equal to minus infinitive to infinitive 1 by 2 delta of t minus of 2 dt. 1 by 2 is outside, minus infinitive to infinitive delta t minus 2 dt, and you know that if I integrate the shifted impulse function, the area in the curve is nothing but my 1. Okay, just a minute. Okay, so that's what impulse function representation and impulse function denotion, operation on impulse function is. Let's take a function, application of impulse function. So let's take another heading, it is the application. Of impulse function, and is one of the most important point that you have to take care of. Suppose I have x of t. Let's take suppose I have x of t. This is from minus infinity to plus infinity. Where, yes, it is 1 by 2. Because the area in the curve is 1 by 2. Now let's see. Suppose I have an x of t, and x of t is now, what I'm doing is that, let's say multiplied by a 3 impulse function, okay? This is 0, this is 0, this is 0. So one impulse function exists at, let's say, here, at t is equal to 0. One impulse exists at here, and one impulse exists at here. Let's consider this to be a t, capital T, and this is minus t. Okay, so what you will write? You will write this to be a delta t. This is delta t minus t, and this is delta t plus t. This is delta t, this is delta t minus t, this is delta t plus t. Now suppose I am multiplying, means basically I am multiplying x of t with delta t, x of t with delta t minus t, x of t with delta t plus t. What you will get? See here. Let's multiply this, call it to be A, call it to be B, call it to be C. Let's do it. Let's take the result outside. See here, this function is purely defined from minus infinitive plus infinitive, but this function only exists at t is equal to 0. Everywhere it is 0. Everywhere it is 0, only exists for t is equal to 0. So this means that what this function is that, suppose I have x of t is now multiplied with delta t. Okay, I will get the value, see here, I will get the value only at here, at t is equal to 0. See, only at the t is equal to 0, and at this value, what should be the value? The value is x0. The value should be x0 at t is equal to 0. What is the value? x0. So what I will get? I will get, see here, I will get a function whose height is now x0, but the existence is at t is equal to 0 only. This means that it is also a delta t. Yes, yes, it is at center. So the existence is still at t is equal to 0. The existence is still at t is equal to 0, but the point is that it exists only for t is equal to 0. So this means that this is also impulse. So what is the nature is x0 times delta t. x0 times delta t. See here. So what I am saying is that when you multiply by the impulse function, you will get an impulse. Surely you will get an impulse, but the impulse height is now modeled by x0. Similarly, second one. See, everywhere this function is 0 except at t is equal to t. And at t is equal to t, see here, at t is equal to t, if you see, at t is equal to t, then I will say that this is the function. See, this is at t is equal to t. So this value is x of t. X of t, and this value is x of minus t, x of minus t, x of minus t. So tell me what you will get. You will get surely again an impulse function. B, this is A. What should be the B? B is also, that is x of t multiplied with delta t minus of t. X of t multiplied with delta t minus of t is also an impulse function present at capital T. Impulse function present at capital T whose height is delta x of t. Okay, whose height is x of t. What I am saying is that, listen carefully, if you multiply this function by this function, then surely you will get an impulse function whose height is now x of t. Similarly, C part is that suppose we have x of t multiplied with delta t minus t, t plus t, sorry, then this is a function which exists at minus t. See, this is the function, this is 0, this is capital T, this is minus t. This is the function which exists at t is equal to minus t. But this is an impulse function. This is an impulse function which is at t is equal to minus t. So what? How you will say? You will say that it is delta t plus in general, what I am saying is that x of t is multiplied with delta of t plus or minus alpha, where alpha belongs to a real number. Alpha belongs to a real number. Okay, then the result is what? X of, see, when you take delta t plus alpha, impulse excited minus alpha. If you take the delta t minus alpha, impulse excited alpha. So this means that it is minus plus alpha delta t plus minus of alpha. Do you understand my point or not? See here, this is the value. This is the value where impulse exists. Value where impulse exists. Value where impulse exists. That's what the meaning. See here, this is the value of the impulse. So if you take the area in the curve, then the impulse value is this one. Okay, that's what the very important point is. Let's say, consider an example. Suppose what I'm saying is that, see here, suppose I have t square plus 4t plus 4 is a function multiplied with delta t minus of 3. What is the result? I am repeating it by one example. Understand it? T square plus 4t plus 4 into delta t minus 3 is what is the result that I am getting. See here, it is, put t is equal to 3 here, it is 9 plus t is equal to 3 here, 12 plus 4 into delta t minus of 3. So that it is 16, 9, 25. 25 delta t minus 3 is the answer. This answer. Okay. So that's what the meaning of x of t multiplied by delta t minus of 3. This property we call it to be a application. This property we call it to be the first property, which I am calling it to be a product property. Product property of impulse function. Okay, so this we call it to be product property of an impulse function. Is it clear? So this is what the product property of an impulse function. Now the second property is very interesting. It's just a representation, same thing. It's just a same, that's the extension of this property. We say that x of t, we say that x of t is multiplied with delta t plus alpha. We get x minus alpha, because impulse exists at x minus alpha, t plus alpha. Suppose someone asks you what is the area in the curve of this function, both the side. Taking the area x of t delta t plus alpha and dt, it is minus inverted to infinitive. I will get x minus alpha delta t plus alpha dt. Okay, and since x minus alpha is a constant, is a value, is a number, so it is equal to x minus alpha minus inverted to infinitive delta t plus alpha dt. And we know that the shifted impulse function area in the curve is 1. Just now we have derived. So this means that this is equal to x minus alpha. That's an interesting, very important point. This is a very important point, and many time number of questions are asked from this property itself. Similarly, this is the A. Similarly, let's call it to be B. Suppose I have x of t multiplied with delta t minus of alpha, and now taking the in the curve directly I am writing, then what it is equal to minus inverse to infinitive. See, it becomes product property from product property x of alpha delta t minus of alpha into dt, and x alpha is outside, so it is the x alpha, it is minus inverse to infinitive delta t minus of alpha dt, and this comes out to be x alpha. Okay, so this is what dt is x alpha, and if C is same property x of t multiplied with delta t dt, what is the result? It is x0. It is x0. D, same extension. Suppose I have minus inverse to infinitive x of t multiplied with delta of alpha t plus beta dt. What is the result that I will get? I want answer from you. I want answer from your side. What is the result that I will get if suppose I have x of t, which is the delta of alpha t plus beta dt? Come on. Yes, see here. What the result? See, the same thing can be written as minus inverse to infinitive x of t into delta. I am taking alpha to be common. It is t plus beta by alpha dt. Since we know that delta alpha t is what? 1 by mod alpha delta t. So just take this alpha to be common. It is 1 by mod alpha minus inverse to infinitive x of t delta t plus beta by alpha dt. Hello Hemant. Yes, come on. X of t delta t plus beta by alpha. Where impulse exists, put this t plus. See, how will you know that impulse where the impulse exists? Put this t plus beta by alpha equal to 0. T is equal to, automatically you will get minus beta by alpha. And since you are integrating, this means that you are taking area. This means that is a 1 by mod alpha. Put t as x of minus beta by alpha. This is the answer. Let's take an example. Suppose we have minus inverse to infinitive e to the power 3 t minus of 2 delta minus 2t plus 4 dt. Someone asks you to find this integral. Can you find out this integral? Come on. E to the power 3 t minus of 2 delta t minus 2t plus 4 dt. Easily you can find out. Come on. Yes, see, sir, first solve minus infinity to infinity e to the power 3 t minus of 2 delta. I am taking minus 2 be common, it is t minus of 2 dt. Then since this impulse, you know that just now I have written delta of alpha t is 1 by mod alpha delta t. Then this comes out to be gen mode. Please concentrate on class. I have just told you what should be there. It is 1 by mod minus 2 minus infinity to infinity e to the power 3 t minus of 2 delta t minus of 2 dt. And what? Where is the impulse? Come on. It exists at t is equal to 2. It exists at t is equal to 2. So put t is equal to 2 here. What you will get? 1 by mod minus 2. Put 2. It is e to the power 3. 2 minus 2. And 2 minus 2 becomes a 0. So e to the power 0 becomes a 1. So answer should be 1 by mod minus 2 or 1 by 2. Very lallu problem. Very lallu problem it is. Okay, now what about this one? See, suppose instead of taking the indefinite integral, these are indefinite integral, let's talk about definite integral. Suppose I have minus 3 to 4, some function sine 3 pi by 4 t delta minus 5t plus 50 dt. Suppose someone asks you this problem. Now I have a limit between minus 3 to 4. Now how to handle this indefinite integral? Mind it. Listen carefully. How to handle this indefinite integral? We will handle this indefinite integral by just checking the limit of this impulse function. If this impulse function exists between this limit, then only we have to consider the function, otherwise answer is straight away 0. For example, this can be written as minus 3 to 4 sine 3 pi by 4 t delta minus 5 common, it is a t minus of 10, sorry. Now this should be outside 1 by mod minus 5. It is minus 3 by 4 sine 3 pi by 4 t delta t minus 10 dt. Now tell me, where the impulse exists at t is equal to 10. See, where the impulse exists, t minus 10 should be equal to 0. T is equal to 10 is the impulse. My question to you is that, will it lie under this limit? Is it lying under this limit? The limit is from minus 3 to 4. But your impulse exists at this point. This means that the product itself is 0. Function exists between this one, you are integrating between this one, and you are integrating between this limit, and the result, this function exists at this point. Okay, so this means that what is the answer? Answer is straight away under 0. Answer is straight away 0. Okay, so whenever there is a definite integral, then you have to take care that whether the limit lie or not. Suppose if lie at the 4 or -3, both the limits are also inclusive. This means that had it be 4, if it is t minus of 4, then the answer will be there. Answer will be there. Okay, because ideally we define the function that it exists at a certain point. It exists at 4, it exists at 0, it exists at 3. Though practically it is not possible. But the point is that, see here, this answer will be inclusive if it is 4. T minus 4 or t plus 3, whatever, this should be the answer. So if the function lies between in this limit, then only you will say that this exists. Okay. So what we have covered till now, we have just defined. There's one more property of impulse function. There's the approximation of a function by an impulse. But that's a very interesting, important and a long property. So we are not going to cover in today's class. We will cover in this Monday. The next class will be on Monday. So but just revise that what we have covered. See here, we have covered. So summarize this one. We are summarizing this. See here, we have defined impulse, did operation on impulse, and third we covered the application of impulse, in which we covered product, property and area property. One more property is there which is very interesting, which is the approximation property, that we will cover in the next class. And hope that these points are clear to you. These points are very, very important minded. These points are clear to you. Today's class is one of the most differentiation of the impulse. These are one of the most important point that we have covered in today's class. Okay, and hence with this, thank you very much. So we will meet in the next class at, let's say, 7 to 8:30 daily, Monday to Friday, guys. Those who haven't covered the complete topic, go and please cover the whole topic. Okay, this is one of the most important subject, and it's a very scoring subject minded. You will get full out of full marks in your GATE examination if you cover the concept thoroughly. Okay, so with this, if you have a doubt, that do ask the doubt. Whatever you feel, just write in the comment box. Okay, and please share this guys lecture, these quality lectures to most of the students, and we will meet in Monday next week. Thank you very much.